In the last video, we were using Kepler's third law in order to help us to derive or figure out an equation for the mass of a star. And so the way we would sort of weigh a star, now keep in mind I used a bit of sloppy notation by saying weigh, we're technically finding the mass of the star. But if you want to find the mass of a star, all you need to do is look at something that's in orbit around it, in this case a planet, and if you know the orbital period of the planet, and if you know its orbital radius, that's not always so easy to tell. But if you know the period and orbital radius of something going around in orbit around an object, then you can find its mass. You can calculate what its mass is. So let's take a look at a real example here. We'll take a look at our own sun. Now the Earth takes 365, it's technically 365 and a quarter and a little bit, but we'll just assume it's 365 days to orbit the sun. And it has an orbital radius of 150 million kilometers. By the way, that is the definition of 1 astronomical unit. That's technically how we do it there. So again, so we have the sun here, which is going, well, it's in the center. And we have the Earth, let's say, that's going around in a nice, we're going to assume it's a circular orbit, even though we know it's not exactly. And it's going to have an orbital radius here of that number right there, that's the radius. We know that the time it takes to go around is 365 days. Now we're going to use this equation then. M is 4 pi squared over gt squared times r cubed. So I'm just going to write that down then. So that's what we're going to need to use. M equals 4 pi squared over gt squared times r cubed. This is sort of what we're looking for here. We're going to calculate the mass of the sun. But that means we need the radius of the sun, so not the sun, the radius of the orbit, but we don't need it in millions of kilometers, we need it in meters. And this period, we need this in seconds. So the hardest part, I think, about this is just doing some conversion of units. So let's take a look at this then. This is a little trick that my chemistry teacher taught me, but I think it's a really good one. So let's just say we have t equals 365 days. What we're going to try to do is multiply or divide by numbers that basically get rid of the days here. And I know that if I multiply this by, turns out, something with days on the bottom, then the days are going to cancel out. And that's the whole purpose, is to get the days out and get another unit. And keep going until you only have seconds left on the top. Well, I know that there's something in a day. It turns out I know that there's 24 hours in one day. So if I multiply this number by 24, I would have then my answer in hours. But I don't want that. I want to keep going. I want to get rid of hours. So how do I get rid of hours? Well, I know that there's 60 minutes in 1 hour. By putting the 60 minutes on top and the hour on the bottom, I get rid of hours. See, had I done the 60 on the bottom, I'd have hours times minutes, which isn't useful to me. I want to get rid of hours. And I don't want it in minutes, I want it in seconds. So I'm going to keep going. I know that there's 60 seconds in 1 minute. I know that technically this is a 1 here in each of these. But dividing by 1 doesn't do anything exciting. So I would cancel out the minutes, so I'd have 365 times 24 times 60 times 60. So I would have some number here. So my period then will be, well, maybe I'll get out my calculator here and figure this out. Whoops. So I need my little calculator. And let's see here. I have 365 times 24 times 60 times 60. Now, if you've done this a lot, you'll sort of memorize that there's 3,600 seconds in 1 hour. That's just because 6 times 6 is 36, and throw 2 zeros at the end. But this is how we can do it. So we have an answer of, let's do this in scientific notation. So 3.1 times 10 to the 1, 2, 3, 4, 5, 6, 7. So 3.1 times 10 to the 7 seconds. Well, let's say 3.15. We'll use a few more decimals. Well, that was useful. We also needed to convert the time, the radius here. So the radius, that was 150 million. Now what does a million mean? That's times 10 to the 6, and that's kilometers. But if I want to use the same method here, I want to get rid of kilometers, so I'll do something with kilometers on the bottom. Turns out I know that there's 1,000 meters in 1 kilometer. If I do that, this is what I get. So I could say it's 150 times, well, 10 to the 6 times 10 to the 3, I could say. So that would give me 150 times 10 to the 9, I could say. And if I want, then I can make it even simpler, I suppose, and say R equals, that's a 1.5 times 10 to the 11. Because I don't want 150, I want 1.5. So it turns out this is the same. So I can use this value here to put it into R, and I can use this value here to put that into T. And don't forget that G, I'll do it over here then. Don't forget that G is 6.67 times 10 to the negative 11. So that may seem really complicated, but it's totally doable. Maybe I'll just write it all out just to make it really easy to look at so that we don't make any mistakes here. So therefore we have m equals 4 pi squared divided by 6.67 times 10 to the negative 11 times 3.15 times 10 to the 7, all that squared. It's important to not forget to square it. And then on the top we have times 1.5 times 10 to the 11, and all that is cubed. That's going to give me my mass in kilograms. So again, I can get out my trusty calculator. There are so many ways of doing this. Okay, lots of people have different ways of doing it on their calculator, and that's just fine, as long as it works for you. Me personally, I like to take, let's say I'll figure out the bottom, I'll figure out the top, and I'll say top divided by bottom. So in this case, and what I'm going to do, I like to use a little store function here. But again, there's so many ways of doing this. I'm going to start off with the most complicated looking thing, the 1.5. I'm going to say times 10 to the 11. I'm going to say enter. That's this. I want this thing, I want to the power of 3. You see that now I've taken care of this. That's what this is here. I'm going to multiply that by 4 pi squared. So times 4 times pi, and do that squared. Press enter. That's the top. So what I personally like to do, so I don't have to write all this down, I'm just going to store this answer as A here. That's just a lazy way to do it. So now if ever I want to use the top value again, I just go back and call up A. There's so many ways of doing this. I'm sure you have lots of ways of calculating this, and that's just fine. I'm just showing you how I often do it. Now I'm going to work on the bottom here. I'm going to take this one that was squared, the sort of most complicated looking one. So I'm going to say 3.15 times 10 to the power of 7. I'm going to take that answer and I'm going to square it. Okay, there it is. I'm going to take that answer and multiply it by this. So 6.67 times 10 to the negative 11. As long as you're really careful with your calculator, it doesn't matter how you do it. So I'm going to store that as B. Then I know that my answer is just top divided by the bottom. So in this case, it's going to be A divided by B. And I get an answer of 2.0 times 10 to the 30. So that's going to be my answer here. So M is going to be equal to approximately 2.0 times 10 to the 30 kilograms. That's going to be my mass of the sun. And you know what's really cool? The accepted value for the sun, the value that you'll find in a lot of textbooks, is actually 1.99 times 10 to the 30. So you see that even our really sort of crappy assumptions here, our assumptions, assuming a circular orbit, assuming all this, assuming it's 365 days instead of a quarter, even all that stuff gets us a really close value to the accepted super duper value of this. I think that's really, really interesting. So this is how we can sort of weigh a star. We can do that by looking at things in orbit. And in the next series of videos, then I'm going to be showing you how we can use this same idea to weigh all sorts of other things. So instead of just stars, we can weigh all sorts of things, including black holes.